Simple harmonic motion, everything you ever wanted to know about things going around in a circle, or a mass going back and forth on a spring, or a pendulum, or even a ball rolling around inside a dish, and so much more, including a brand new use for trigonometry. We remember trigonometry, trigonometric functions. They take angles and turn them into numbers or ratios. Inverse trigonometric functions, they take numbers and turn them into angles based on the sides of right triangles. SOHCAHTOA. We remember that. We use them for two main functions. One, to take a vector and break it into its components. Could you break those 35 meters at 37 degrees north of east into a northern component with the sine function and an eastern component with the cosine function? Bet you could. Number two, we are taking two components and using them to create a vector. Could you find the angle with the arctangent function? Could you find the hypotenuse of this velocity triangle here using the Pythagorean theorem? Yep, we're moving fast. A brand new use for trigonometry, connecting something else from Physics 101, and that is circular motion. Circular motion, there's a bug on a record player. That bug on the record player is moving in the wrong direction. I'm not changing that. It's moving in the wrong direction, going about 60 degrees. We could talk about the bug's location in terms of X and Y. Easier just to say that the bug experienced 1/6 of a rotation, 60 degrees, or we could express that same angle in radians. Radians, the ratio of the arc distance traveled to the radius. A more natural way of talking about angle. Nothing against the number 360. It's a great number. Radians a little bit more natural, and we could say that 2 pi radians corresponds to a complete revolution, or 360 degrees, meaning that 60 degrees is about equal to 1 radian, closer to 57 degrees, kind of close there. And if you have a bug moving an angle theta in radians in a particular time, you could talk about its angular velocity. This is not a W. This is omega. Angular velocity, change in angle per time. I know what we can do. We can talk about this bug going from position 1 to position 2 in terms of its frequency. Frequency defined as the number of cycles per second. That was some high frequency clapping. Frequency is equal to the inverse of period, the time for one complete cycle. All right, now stay with me here. One cycle is equal to 2 pi radians. So 2 pi times the number of cycles per second is equal to the number of radians per second. For every cycle you get 2 pi radians, so you could say that omega is equal to 2 pi f. Angular frequency. Wait a minute, I thought omega was angular velocity. Angular velocity and angular frequency, they're friends. Omega. And that can be kind of confusing because frequency and velocity aren't the same thing, but angular frequency and angular velocity kind of, sort of, definitely are. Let's talk about this in terms of a race. Bug 1 and Bug 2 are racing around the record player. They go the same angle. Look at Bug 1 and Bug 2. They start looking upwards, and at the end of the race, they're looking kind of up and to the left, so they go the same angle. I hope you agree that theta 1 is equal to theta 2. What about the radius? I hope you agree that the radius to the center of rotation for Bug 1 is less than the radius for Bug 2. What about their arc distance? Well, Bug 2 traveled a greater linear distance, S for arc distance, and that means that they did it in the same time. The Bug 2 is traveling with a bigger linear velocity. Bug 2 is going faster, but both of them are traveling with the same angular velocity, the same omega, the same angular velocity, going the same theta in the same time. They are traveling with the same angular velocity. They are traveling with the same frequency. They will make the same number of cycles per second, and they are traveling with the same period, the same amount of time for one cycle. Well, that's a lot. 1, 2, 3, 4, 5, 6, 7 equations there for two bugs. But that is true not just for turntables, but also for springs and pendulums and other things. They make waves. Think about the X position or the Y position of this bug. It's going up and down, or left and right and left and right. It's a wave, and that means we can express it with a wave equation. Y equals a sine theta. And theta keeps changing. And that means, yes, you will have to be prepared to use the radians setting on your calculator. See if you can solve this sine problem and this arc sine problem here. And sine works just as well as cosine. We're using sine most of the time for displacement, but we could use cosine. You got that? Good. If y equals a sine theta, then why not just say that y equals a sine omega t? A stands for amplitude. Hey, you think that the blue bug had a bigger amplitude than the red bug for that race? Yes, they did. Anyway, y equals a sine omega t. Theta equals omega t, and we're rolling, or we could even say that y equals a sine 2 pi frequency times time. Now, with your permission, I'd like to move away from the turntable and towards the pendulum. I think what I'm talking about now is easier to see with the pendulum. We have places, times in the pendulum's life where the displacement is a maximum. And remember that the slope on a position versus time graph, also a displacement versus time graph, same thing. The slope here is equal to the value of the velocity. In other words, at a time of maximum displacement, you will have zero velocity. When your displacement is a maximum, you will have zero velocity. And that happens a lot. These are the turnaround points. You're going one way, then you turn around and go the other way. Similarly, when your displacement is zero, that's when your velocity is a maximum. That's when the slope on the displacement versus time graph is greatest. Again, you're a pendulum. When you're way off to one side, your velocity is zero, your displacement is a maximum. A little bit later, your displacement from the central location, your displacement is zero, and your velocity is a maximum. That's where your velocity is a maximum. And then your displacement is maximum in the other direction, but your displacement is maximum again, and your velocity is zero. Then this goes back and forth and back and forth, and a period is a complete revolution, get you right back to from where you started. So you know you've done a complete period or a complete revolution when you are back to your starting position. And we can also think about energy. Kinetic energy, 1/2 mv squared. Kinetic energy is a maximum. Where is it a maximum? When your displacement is zero. This is the spot where your kinetic energy is a maximum. Your kinetic energy here is zero. You have zero velocity, zero kinetic energy. And if you can think about kinetic energy, we can think about potential energy. Also, in this case, gravitational potential energy. A spring, of course, would have spring potential energy. Here, gravitational potential energy is a maximum. Here it is zero. Again, zero gravitational potential energy here, which is there. And then here, we have maximum gravitational potential energy, but I don't get that equation. I thought gravitational potential energy was equal to mgh, and here you call it 1/2 kx squared. What's going on there? We don't really have time to go into it. And also, is this a circle or is this a parabola? Those are good questions. Turns out that for small amplitudes, the circle and the parabola become really good friends. Wish we had more time to talk about that, but we don't. Anyway, we are a pendulum going back and forth, and that's right. We everywhere conserve total mechanical energy. In other words, kinetic energy plus potential energy everywhere is constant. Conservation of energy, something you might remember from the first course also. And if we're talking and having fun with position and velocity, how about we get acceleration into the ball game here? It's another wave. Turns out the slope of a wave is a wave, and the slope of a wave is a wave again. Start with this position. Displacement is zero, velocity is a max, and we are not accelerating at this point. That corresponds right there. A little bit later, a little bit of a different situation. Here, displacement is a maximum, velocity is zero, and your acceleration is a maximum, but you are accelerating in the opposite direction of your displacement. Yeah, that's a lot. But you can see that if the displacement graph is a sine, velocity graph is a cosine, and the acceleration graph is a negative sine graph, because the acceleration and displacement are always fighting against each other. Or you could write out the equations like that to get all those coefficients. Requires a little bit of calculus, which we're not touching. But we will notice this, that the maximum possible velocity is 2 pi fa, also known as omega a. And if you look at that equation for velocity, whether you're talking about sine or cosine, your maximum value for sine or cosine is 1, so your maximum possible velocity, and this equation even makes a little bit of sense. The bigger your amplitude, the faster you're going to have to go, and the bigger your frequency, the faster you're going to have to go, so that makes sense. And there's our equation for maximum possible acceleration, and we can use that to derive some equations. Turntables, then pendulums, now springs, and Newton's second law, another old friend from the first course. Anyway, we say that this spring has a restoring force K. That's the spring constant K. So The more you stretch a spring, the more it's going to fight against you. The more you compress a spring, the more it's going to fight against you. Anyway, stay with me. So the maximum possible acceleration occurs with the maximum possible stretch, a little bit of rearranging, and a little bit more rearranging. And there's our equation for the frequency of a spring mass system. And this equation, I know I went through that quickly, but it makes a little bit of sense. The stiffer the spring, the higher the frequency. The smaller the mass, the higher the frequency. That is what Newton's second law is all about, isn't it? Trying to shake a big heavy mass back and forth, it's going to take you longer. You're going to have a smaller frequency if you try to shake a full gallon of milk back and forth. And so that there you go. And here we are with the pendulum again, and we have another equation. This is for the frequency of the pendulum, and notice that the frequency of the pendulum does not depend on mass. Cancels out. We're skipping over the derivation, but the mass cancels out, so that goes away. And also the amplitude goes away too. So when we're talking about the frequency of a pendulum, it does not depend on the amplitude, which is a little bit surprising. But then if you do an experiment like this in a garage, you see that it definitely is true.
Let him go again.
And it's true for many different things, including a ball rolling around inside a dish or anything that turns around and can be modeled with that restoring force that is opposite the displacement and proportional to the displacement. You can get simple harmonic motion, at least over small distances, and life can be good because you can have sine waves and cosine waves and all sorts of fun, and you can model these things with equations like frequency is equal to 1 over period, and angular velocity / angular frequency equals 2 pi f is equal to theta divided by t. And then you can take simple harmonic motion and blast it out into space, whether you're talking about shaking a string or whether you're talking about sound waves and light waves, which gets super complicated, but start with a fairly simple equation. Velocity is equal to frequency times wavelength. Now that's pretty much the simplest equation you could ever have. Velocity is equal to the distance of one wave times the number of waves per second. Velocity is equal to wavelength times frequency, the length of one wave times the number of waves per second. It makes sense. And the velocity of a wave is determined by the medium that it travels in. Here we have two equations, one for the velocity of the wave on a string, and it is faster for a bigger tension string. Mu is the mass per length, so a big tension string with a lightweight rope, that's the fastest type of wave you're going to get. And then the velocity of a sound wave, I love this derivation because it includes gamma. And what is gamma? Gamma is the ratio of the molar specific heat capacity of a gas at constant pressure to the molar specific heat capacity of a gas at constant volume, which is, again, something we talked about in Physics 101, and like, what is that doing in an equation for the speed of a sound wave? And that's great, but it also depends on temperature and the mass of the molecules, the type of gas that is supporting that sound wave. The key here is that the velocity of the wave depends on the medium that the wave travels in. The frequency of the wave, what does that depend on? We already told you. It depends on, for the spring mass system, it depends on the mass and the spring constant or the spring stiffness. For the pendulum system, it depends on the acceleration due to gravity and the length of the string. The frequency of the wave depends on the source of the wave. That simple harmonic motion stuff, those were the sources of waves. Hit a drum. The simple harmonic motion, the sine wave type motion in that drum, that musical instrument is producing sound waves, and you're good. Velocity depends on the medium, frequency depends on the source, wavelength, lambda, depends on the combination of those two things. And we could say that a high frequency wave has a shorter wavelength and a low frequency wave has a longer wavelength. But what does this have to do with sound waves and light waves? What it has to do is that these things that seem like they have absolutely nothing in common are totally connected by the laws of physics, totally different and yet definitely kind of the same in a way. Sound waves are mechanical waves that need a medium. Light waves are electromagnetic waves that can travel in a vacuum. More about electricity and magnetism later in this course. Sound waves are longitudinal. Light waves are transverse. Sound waves are created by vibrating objects. Light waves are created by vibrating electric fields, also known as currents. Different frequency sound waves give you different pitches. Different frequency light waves give you different colors. Sound waves travel much slower, about 1/1,000,000th the speed of a light wave. But they obey this fairly straightforward equation. Velocity is equal to frequency times wavelength, which explains why I got woke up this morning by this sound. And I know exactly when that train is the closest it gets to my window. Listen again. How do I know when that train gets the closest to the window? It's not just that the sound gets louder volume, it's that it changes pitch, and that's what's known as the Doppler effect. Hey, look, we talked about longer wavelengths, lower frequency, shorter wavelengths, higher frequency, and these waves created here by this moving source get mechanically pressed together, and we see that equation in action, and we are on our way.